It's a really exciting time in the field, as many of you might know, broadly around AI. And it's exciting because we're building, I think, these very interesting technologies. I'm going to check on my slides. There we go. Okay. So we're building these, I think, quite interesting technologies. And I think asking new questions about how we measure what they're doing and whether they're effective. And so my goal today is to talk a bit about some of the work in my group that's trying to engage with this question and hopefully bring together a few different threads to think about how we can move the needle forward in terms of measuring AI systems. So I think there's a fascinating history on AI measurement, all the way from Okay, so AI measurement has a fascinating history, all the way from arguably where some of this started. So these are a picture of old punch cards at Bell Labs, where Hingelman was working on trying to build some of the first benchmark systems. So the idea was to try to train algorithmic systems to recognize alphanumeric characters based on these punch cards. I don't think punch cards have been around for a long time, but some of you might recognize them. And I think this has moved on from these early times to really a big part of the practice within the AI field. And I would argue that this process of benchmarking evaluation really is a superpower of the AI community. And sort of when our goals well aligned with benchmarking, I think we've found real meaningful and exciting progress. When our goals are not aligned, I think things get a little bit tricky. So in particular, one of the things, or many of the things that the AI field is extremely good at is when we have some kind of measurement process that's repeatable and scalable, and then we can also, as a community, go at improving that number, whatever that number is. I think more than any other thing, the field really likes to do this. And so some of what I'm going to talk about today will be to engage some of these norms and then hopefully lead to better outcomes. Some of this has been noted. So there's a interesting, and I invite you to take a look if you're interested, paper in the CACM in 2012 by David Patterson, titled "For Better or Worse, Benchmarks Shape a Field." He was talking broadly about computing, but I think this is as much a pattern in AI as it is all across the whole field. And the argument here is that benchmarks have this power to capture both the vision, but also the excitement of a field towards a shared goal. And particularly in computing, what it's done and what it continuously seems to be able to do is to get us to sort of work hard towards some kind of shared vision, some shared outcome. And so the field has worked on building benchmarks for a long time. I think around here, there's some signals that we do some things really well when we think about evaluation and benchmarking. And so some of the things that we do are, for instance, observations about internal statistical validity. So this is the question of, if I build some kind of benchmark or measurement process, do I expect the results to stay the same if the conditions are roughly similar? And what we found over and over again, and this is a little bit surprising because statistics actually suggest that it shouldn't work as well as it does. But there's a bunch now of both conceptual understanding and practical understanding that suggests that benchmarks actually work pretty well in terms of internal validity. So if you repeat some kind of measurement process, change the data, but the conditions are similar, the kinds of results you get seem pretty consistent, which in some ways could be surprising, but actually is a good outcome. Another interesting observation is external statistical validity. So this is the question of actually meaningfully changing the conditions of the system that you're building and asking which models are thought of as better or worse, so some kind of ranking across models. And again, I think there is a surprising observation, surprising to me maybe, that many of our AI evaluation processes are actually pretty good in terms of, again, this kind of external validity. So a lot changes in the world. The models that are thought to be better still seem better compared to models that are thought to be worse, even though the situations are actually meaningfully different. And so there's an interesting paper by Wally Salahuddin and Maritz Hart that talks about doing ImageNet intervention. So they take this ImageNet, which is a large data set for computer vision. They change a ton of stuff, and they ask which models are better or worse. And the ranking actually stays consistent over many, many years. This is, this work in 2024, the original ImageNet paper, many more years, more than 10 years before that. And again, seeing quite stable statistical patterns over this long period of time. So one example of a benchmark, and one that's maybe a modern benchmark that, to give you a sense of how these things are built and how we'd like to use them, is the graduate level Google Proof Q&A benchmark. So often summarized as GPQA. So there was a lot of effort that went into building the benchmark. The first step was to write the question. So question writing is the first step. From there was an expert validation step where a bunch of experts looked at all the questions and they asked about issues like agreement, issues like correctness, many of these kinds of validation of the data sets. And then there was a question revision step based on the choices to sort of better align with, again, hopefully correctness of those questions that were being developed. After that, one more validation step that then checked again that all the benchmarks were correct. And then they had non-experts take a look at it and see to what extent could they answer some of the questions in the benchmark. And so the idea here was to try to get a good sense of what questions here were really hard and were tied to some scientific knowledge. What questions could people answer either unsupported or maybe even using a little bit of Google usage. And so they found, for example, that experts had reasonably high accuracy. So this is in 2023, somewhere around 60 to 70%. Non-experts, roughly around 34%. So this is, graduate level chemistry, graduate level science questions. So these are hard questions. And then GPT-4 at the time had a 40% accuracy. And so from there, you could try to ask what kinds of claims we might make. And in particular, looking at what claims the original benchmark, GPQA benchmark made. And so one claim that's maybe straightforward from the experiment is to say the results of this experiment, or actually said differently, suppose we have a model that scores really well on this benchmark. One claim you could make is that this model does a good job of answering graduate level Q&A questions in biology, chemistry, and physics. So this is maybe a reasonable inference because this is what the test is actually designed to measure. However, you could imagine making a bit more ambitious inference. And so what I'm showing here is a blog post from our friends at Anthropic that cited the GPQA benchmark, but additionally, I don't know if it's easy to see here. Okay, I could make that better, but I'll just go ahead and put the claim up. The claim that they ended up making was this model has reached graduate level reasoning in some scientific domain. These are very different claims. The first claim is a sort of very direct claim about what the test was designed to measure and what it says. The second claim is a broader claim about some kind of outcome that says something about deeper intelligence from the model. And so hopefully you might agree with me that claim one is very reasonable. Claim two is a little bit trickier, may or may not be reasonable. Or maybe a bit more scientifically, claim one is more supported by the evidence of this benchmark than claim two is. So claim one being, again, the model can answer Q&A questions, claim two being graduate level reasoning. Now, within the field, some of this has been observed. However, I think most of the focus on building benchmarks has been on questions of correctness and statistical quality. So there's a bunch of work thinking about content validity and data correctness. I'd cite some interesting work looking at MMLU, which is one of the very popular benchmarks for large language models. And here they're mostly showing that there are systematic mistakes in some of the questions, some of the work that they can do to help fix it. There's also a lot of worry and interest in what is called benchmark saturation. This is the observation that benchmarks often start off hard for many AI models. So start off in the, for example, 30, 40%. But within a few months, maybe a year, the best models end up in a 90% performance many other benchmarks, which again is something that causes some concern and something to work on within the field. That said, what I'm going to share and argue today is a little bit different. I want to argue that I think we're actually facing a meaningful crisis of measurement within the AI field. And there are lots of signals that this is happening. So one of this is engagement in policy. So there's a bunch of work around policymaking that uses the results of benchmarks to ask and answer questions about the riskiness of models, say both in capability and safety evaluations. There are a variety of high-stakes deployments that anchor on benchmark signals to make decisions about whether a model should be part of a healthcare decision-making stack, whether a model should be part of legal, part of other kinds of decision-making stacks that have meaningful real-world consequences. There are significant resource investments of the order of hundreds of billions of dollars that are directly guided by the results of what models do on certain benchmarks. And arguably a lot of public thinking about how much to trust models and what to say about what models are doing are guided by what the community has said about what benchmarks are measuring and what we're seeing from these models. And so one argument, and an argument I'll say posit here, is that there's quite a big gap between what the benchmarks were designed for and what role we're asking them to play now. And in particular, benchmarks were generally designed for sort of within-field model evaluation, in some ways maybe research competitions, but really weren't designed to help answer high-stakes decision-making questions. But we're using them more and more for these kinds of applications. So some of this has been noticed. There was some work in the AI index. This is 2024. I forgot to add the year, where Anka, who's here somewhere in the back, did a bunch of work looking at the state of responsible AI, and as part of this work, was asking questions about what the benchmarks were measuring. And Nestor, who's also here, was interviewed by New York Times, where he said the lack of standardized evaluation makes it extremely challenging to systematically compare the limitations and risks of various AI models. And so again, there's a more public acknowledgement of what it is the benchmarks were designed for and what it is we're asking them to do today. So along these lines, I want to share mostly three ideas that I think could help move the field forward. First is a discussion around measurement validity. So how we think about specific claims around measurement and ways that we can help better engage in what validity might mean for various kinds of measures. Next, I want to talk a bit about advancing tooling for improving AI measurement science, using some ideas from psychometrics. And then finally, I'll talk a bit about predictability of model interventions, and I'll use some ideas from some of the work we've been doing. Outside of that, I'll also wax poetically about some open problems in future research and some thinking that we've had about where some of this might fit into governance, policy, and decision-making more broadly. Okay, so first on this question of validity of specific claims. I think measurement plays a quite critical role in the ecosystem and civil society broadly. And one of the roles that it plays is there's this conversation that needs to happen between technology builders and broader stakeholders, so policy, governance, and decision-making. And for a variety of different reasons, often what ends up being critical to this conversation is some notion of quantifying what technology is doing. And often measurement is what ends up playing this role. And so in my view, measurement actually ends up being a critical part of closing the gap between technology building and then broader civil society questions around policy, governance, and decision-making. And in particular, I think validity is interesting as a way to frame what we need from measurements and help us critically engage with the outcomes of measurement processes. And so I'll talk a bit about some work we've been doing. There's yet another QR code. There's a lot of QR codes over the course of the hour. For a paper you can look at if you're interested, will be online soon with some amazing students and friends of my group, where we've been trying to think through what does a validity framing look like for the AI ecosystem. To help frame the question, and a lot of our thinking on this has been guided by existing work in psychometrics. So for those of you who are either in psychology or familiar with some of what has happened in that field, in the 50s, there was arguably a crisis in the psychology literature. And a lot of this tied to the framing around questions like intelligence, very much like what we're asking now of AI systems. At the time, psychological tests, intelligence tests, were being used for life-altering decisions. However, there was a wide variety of different tests that all claimed the same thing and often gave contradictory results. And so, to that end, there are a variety of players who started thinking much more carefully about what they ended up calling validity theory, notably Crumbach and Meehl in the mid-50s, that talked about validation, not just in terms of the testing procedure, but actually the inferences and claims one is making from the outcomes of that test. And a lot of this moved on all the way through Campbell, Fisk, and Messick, many of which shaped both a lot of what I'll talk about today about framing as a construct and construct validity, but also downstream impacts, thinking about what the validity means when you're implementing tests in the real world. And as mentioned, and as I've argued, I think AI is facing a similar crisis with meaningfully high stakes, arguably as high stakes as some of this earlier engagement in psychology. So the first argument I want to make along these lines is that we should think carefully about evaluations supporting very specific claims. So an evaluation could be some kind of judgment or some kind of decision, and a claim being information from, say, benchmarks or qualitative reports. And so I'm drawing this as a path. Really, this is a really quite messy loop, so things can go back and forth in different ways. But for discussion, I think it's helpful to think about this as a sequence, where we start off with some kind of object of a claim, which is something we care about. So it could either be what is sometimes called a construct. So constructs here are unobservable properties of a system. This could be things like reasoning or intelligence, which we need to define via construction. Alternatively, there could also be a criterion. So these are observable properties of a system. So properties we can observe directly. So these are things like prediction accuracy, precision, recall, standard things you would observe or evaluate in a learning test. And so we start off with some object of a claim, depending on what we're hoping to say. And then we formalize this into a claim, what we want to say about this object, so either the criterion or the construct. So for instance, suppose what we want to say is the model is a great calculator, which arguably many of our arithmetic tests might be inadvertently measuring. So this is fine. This could be a criterion. We know what a calculator should be able to do. You can then check whether the model is actually being a good enough calculator. Or you could imagine trying to make a much more construct-derived claim. So I want to claim that my model is intelligent. This is a different kind of claim. This is, again, this construct, unobservable property of the model. And you need to think through what evidence you need to be able to make a claim like this. And so the last step in this chain is thinking about validation of the claim via things you can actually observe. So for criterions, this is typically easy because, again, the criterion is a directly observable property. For constructs, as I'll talk through, you have to argue and then design a scientific process to go from observables to the underlying construct. And so this could look like what kinds of signals you might need to observe in the world to be able to make this argument about this broader construct of intelligence. So I'll walk through this in an example of a GPQA benchmark and some of the claims that were originally made. So we already introduced this. This is, again, this benchmark for graduate level chemistry and physics. And there's one scenario where the claim you're hoping to make is that the model can accurately answer graduate level specialized multiple choice questions in biology, physics, and chemistry. Now, this is, again, a fairly precise claim. This is a criterion because it's directly observable from the measurement process that you're doing. And so you can just check accuracy on these kinds of questions, and you can infer from there that the model is good at multiple choice questions in physics and chemistry and biology. So this would be the process that you go through. Again, the main evidence you have is actually what the model does on this benchmark. You could then imagine trying to make a different claim, which is something about reasoning. Reasoning here is a construct because, again, it's not directly observable. And so if your claim is this AI model or AI models in general can reason, then you might argue that the evidence that we have is insufficient to support this kind of claim. And so a lot of the work here, and I think the key hopeful takeaway that I'm trying to anchor on is that looking for or trying to work through validity should not be this ambiguous general process. It should be very tied to what kinds of specific claims one is trying to make. And tied to those claims, we need to find evidence that justifies those claims through rigorous scientific processes. Again, I've written this as a sequence. Again, in practice, this is much more, can often be more complicated. You could first, for instance, get evidence. So you run some tests, you see some intriguing results, and you can ask, what kinds of claims could I make based on this test? I think this is also justifiable. Here I'm saying this is sort of the more forward process. But again, the key takeaway, the whole point I'm hoping to anchor on is that the claim that you're trying to make should be directly tied to evidence that you can measure. So looking at what some of the questions you might ask and how you might frame validity, I'll go through again this example of GPQA. And in the work, we go through 5 validity directions tied to a variety of different claims that one can make. Here I'll talk about 2 kinds of claims I just mentioned. One, the criterion claim, which is the model can answer graduate level Q&A questions. The second, the construct version, the model has reached graduate level reasoning. And so the first is content validity. That's the first column over there. And so this asks whether your evaluation covers all the relevant cases. So for claim 1 about graduate level QA, we know the development process of the benchmark. We know that it's expert curated, and there's a bunch of work that's gone through understanding the performance gap between experts and non-experts. And so we'd argue that there's sufficient evidence here to be able to make the claim of content validity for the claim of graduate level Q&A performance. However, if you're trying to make the claim of reasoning, there's some gaps. And the gap here is that the actual evaluation is multiple choice question answering. And the counter argument is multiple choice doesn't test general purpose interaction and reasoning. And so it's a pretty low bar for trying to make a claim as strong as model reasoning. Because the actual thing that's done, and by the way, if you're not familiar, the way that these are again are designed are the model is given a set of potential options. It's asked to pick the right one out of 3 or 5 options. And so the answer is, again, a correct answer out of 5. And the claim here is that that style of measurements, while interesting and useful, is not enough to be able to make a stronger claim about content validity for reasoning. A second direction is criterion validity. So the second column over here. And so this asks whether the evaluation correlates with a known validation standard. And so for criterions, this can be much easier. For claim 1, here we can see that there's human expertise in the benchmark construction, and we also know a lot about what regular people do, so non-experts do in this kind of work. And so we'd argue here that there's good evidence for criterion validity. However, we'd argue that there isn't good evidence for the claim number 2 about reasoning, because there are no other established reasoning benchmarks that have given us enough evidence to be able to make any claims about reasoning in a fundamental sense from AI models. A third and very important one is construct validity. So here this asks whether the evaluation actually measures what we intend to measure. And for criteria, this is easy because criteria are about direct observables. And so the claim here is, we want to observe something. want to check something, we're observing the thing we want to check, and so directly we can see whether the model satisfies criterion validity. However, we'd say that it doesn't satisfy this for reasoning because we're not separating other things that could explain why the model does well for this benchmark. So in particular, memorization would be a good enough explanation for why the model might do well on this benchmark. A fourth is external validity. So this asks the extent to which the evaluation generalizes across environments and settings. So here, for claim 1, the answer is, one way to make this evidence concrete is to ask whether the evaluation mirrors real-world usage, say from human experts and non-experts, and would say that this is satisfied here. However, we'd say that it's not satisfied for the reasoning ask because, again, we only looked at question answering for 3 scientific domains. Again, the evidence that we have is not sufficiently deep or broad to make this broader claim about external validity. And then finally, an important one is consequential validity. So does the evaluation consider the real-world impact of its interpretation and use? And here, some of what we see, I think there's some space for caution. We've already seen the people overgeneralize from what we have already observed from benchmarks. So stakeholders very easily or very often will overgeneralize. And so thinking about how to represent and present the claims in such a way that you avoid this pitfall, I think is quite important. And we'd say that on the claim number 2, on human-like reasoning abilities, we would say the evidence is, again, quite far from being able to justify this broader consequential claim. And so what I've gone through here are 5 broad umbrellas under which we can define a validity framework, and given the example through GPQA to show for some claims where we think they're well justified and when they're not justified. And so one can do this directly on benchmarks. We did a bit of an exercise, and I invite you to take a look at the paper and look at some details. But we looked at a variety of work across benchmarking, say in vision and other areas, and asked how, as the field has progressed, what kinds of validity claims have been made and to what extent those validity claims were justified. And so I'll invite you to take a look, looking at, say, in vision, all the way through early deep learning, all the way to advanced vision tasks, and some of what's happening now in multimodal evaluation. Similarly, one can ask these kinds of questions about language. So in the paper, we do some work engaging in all the way from early rule-based systems to more modern work in large language models, and engage with the kinds of models that are being built, the kinds of questions that are being asked, and the kinds of validity considerations that we think are important for the claims that are being made with existing benchmarks. One more idea that I want to maybe anchor on to, I think is important for thinking through what it means to make claims about validity is what are known as nomological networks. So again, for folks who work in psychometrics, this is maybe a common thing that you might see. And the idea here is to define the relationships between various constructs and how those relationships tie to observables. Again, constructs are unobservable concepts. So again, scientific concepts. You can't observe them directly. You have to make this link between the thing you can observe, generally criteria, and anything you can observe but you want to argue for. So things like reasoning of various kinds, mathematical creativity, computational accuracy, and so forth. And so nomological networks are a device for helping to make these connections between different constructs, to make arguments, and these are done formally, by the way, in psychometrics, to make arguments about how these underlying constructs relate to each other and relate to the observables they can actually see. So a little bit on how you might actually get started on doing something like this. So you generally would start off, one way to start off is think about what the object of the claim is that you're trying to make. And then identify what constructs are related to it. So identify, in this case, nomological network that describes it. And then you can think through the process of establishing constructability based on the network. Or if it's not a construct, if it's criterion, which is, again, much more directly observable, then you could ask whether the criterion is established, tied to an existing standard, or is one that's new, and then you have to sort of do the work to establish it. And this helps define whether you simply need to establish criterion validity whether you need to do some additional work to establish things like content, external, and consequential validity for that criterion. And so we think about this as a sort of useful decision tree for thinking through how one might start actually building constructability for real-world scientific tests. So to summarize the first part of the talk, we think the way to move forward in building this science is to tie validity to specific claims. And on the validity side, we've talked through 5 notions that we think are important for making claims about AI validity, that go all the way from content to criterion to constructs to external and consequential validity. Next, I'll switch gears and talk through some work we've been doing, thinking through some of the tooling that one could build to help better move forward some of the AI measurement practices. And in particular, what I'd like to advocate for is that we can learn a lot from measurement science in other fields. In particular here, I'm going to talk through some of the psychometrics ideas. And for the technical folks in the room, the key technical tooling is really latent variable models. And so latent variable models will be the tools that we'll use to disambiguate factors that explain measurement results, help operationalize some of the nomological network ideas that I talked about briefly. And some of the examples are things like item response theory, latent variable models, factor models, things like that. And so for this, I'll talk through another recent paper, which with a variety of incredible colleagues, is a QR link if you want to take a look at the paper, called Reliable and Efficient Amortized Model-Based Evaluation. So to frame this work, here we're going to look at trying to ask the question of looking at a particular benchmark, looking at the answers that some model gives, so how correct it is, and trying to disambiguate factors of variation that explain model performance in a benchmark. So the standard practice is that I will ask a model a question, get its answer, and check how many answers it gets right. So this is a indicator here is, did it get the answer correct or not? Then I'll average number of correct responses that a model gets, and this will give me a fraction of correct responses from a model. And so this would be a standard way of evaluating performance of a model on a particular benchmark. And so in the psychometrics literature, this would be called classic test theory. Again, look at using average performance as a proxy of the performance of a model. Helm does something. Helm is a measurement benchmark here at Stanford. It does something sort of similar. It uses average win rate, but it gives a very similar kind of outcome. And so some of the questions that we want to answer when we're evaluating models and benchmarks are looking through a variety of different models. So I'm showing here on the vertical axis different models, on the horizontal, different benchmarks. And the question I want to answer is, how well does the model do on existing benchmarks? But I also want to answer, how well might new models do on those benchmarks? So I want to answer similar questions for new models. And I also want to answer, how well might existing models do on new data sets? And so all these are part of understanding the capability of various kinds of models that we might build. And so a standard way to try to do this would be, again, to use average performance and then try to extrapolate from the average performance to what the model might do beyond the existing observables. And so if I do this using classical test theory, using simple averaging, it has some advantages. It's fairly simple. I'm just going to use averaging as a way to get my performance score. And asymptotically, if I get enough examples, statistics say that things should converge well and it should be correct. However, there's some downsides to basic averaging as a way to understand model capability. So one, it requires that there's an overlap of data samples across models. So all the models have to see the same exact examples in order to evaluate them and compare them. Otherwise, I don't have comparable numbers. So it's equivalent to, we're taking a test. We all need to see the exact same test for the instructor to judge who is doing better or worse on this test. And I'll argue in a little bit that this is challenging for many of the AI tasks that we're looking to deploy models on. So in particular, some of the places where this show up are things like agent evaluations, where models take different paths and so answer different questions till the observations are not the same across different models. Various kinds of applications or sort of measurement practices like red teaming intentionally evaluate models using different kinds of questions, because the goal is to understand whether models are fragile. And so again, you have this lack of overlap. Again, I can't directly compare models to each other based on the results. One maybe interesting thing that I think has flown under the radar, but is worth mentioning, is that as the field has progressed, evaluation has actually gotten pretty expensive, and more expensive than I think one might appreciate. So, now we're talking at scale to do a meaningful fraction of the evaluations that people do. Hundreds of thousands of dollars if you want to do this across lots of different models, because we're talking about several thousand, hundreds of thousands of questions. You need API access to all the models. You need sort of compute to run everything. It actually starts to get to be much more expensive than you might think. And so I'll talk a little bit about some ideas from going away from classical theory that ends up reducing query complexity, and so reducing costs for actually implementing evaluation. And finally, I'd say that the direct averaging effect makes it pretty hard to answer questions about interpreting the results and predictability of the results. So there's a bit of progress, but I think early days on this. And so I think we can do this better. And in particular, some of the ideas like atom response theory help improve the state of the art along these directions. A bit more on what's missing in current practice. So particularly for large language models, there's a lot of focus on just ability of the model, so how well they're doing. But actually, what we found is that the difficulty of the question explains a lot about the overall performance. And so somehow capturing something about both the model capability, but also some signal about what the difficulty or how hard the questions are that are being asked ends up being quite insightful about understanding what's going on in the evaluation process. And so we've done a bit of work on this. I'm showing here on the right a very simple experiment where we take a benchmark where we look at a variety of different models and a variety of different questions. We randomly hide some answers to some questions. We try to predict how well the model will do on some held out questions. And we use sort of very naive approach, like average score as a way to check how models are doing. Or we do a little bit of difficulty modeling. And we find that difficulty modeling actually makes a huge difference. So separating out questions based on difficulty. Now I'll talk about how to do this in 1 minute. And so my group has been looking at this idea called atom response theory that comes from psychometrics. And here we're using the simplest version. There are more sophisticated versions. And the idea here is to disambiguate model capability from question difficulty. In particular, it doesn't require overlap across the benchmark data sets, which are helpful for some of the examples I just talked about. And when combined with active learning, we can show that in many cases, it can reduce the number of questions you need to ask. In some cases, we can ask 80% fewer questions to get good estimates of performance and comparison across models. Plus, we do what we think are some interesting things that we haven't seen in the psychometric literature. So we do some work in predicting difficulty of new questions and synthesizing questions that match a target difficulty. And I'll talk through some of this in a second. So a little bit of a technical background. So the thing you get to see is how well the model does in a question. So this is an indicator that the model get the question right or wrong. And a simple latent variable model for this tries to separate out a parameter that we call model capability, a parameter we call question difficulty. And you can do much more sophisticated modeling. We'll stick here with the simplest model. It just says the likelihood of getting an answer right depends on the difference between how good the model is and how difficult the question is. And that difference ends up controlling the likelihood of the model correctly answering a question. And so the thing you want to understand or pull out from this when you look at the data based on this model is an estimate for these two quantities. So how good the model is, model capability, an estimate for question difficulty, and disambiguating both of those directions. So a simple graphical model that sort of formalizes this idea. And so we look at a bunch of data sets from Helm, which is, again, this data benchmark suite out of our colleagues at CRFM. that are a combination of capability and safety data sets, roughly 200,000 questions. And we also look at 172 large language models. There's not a perfect overlap, so not all questions are answered by all models. So there's some missing data. And we score all the responses by whether they get them correct or wrong. I'm showing some basic statistics of the data set that we use. And so the first thing that we checked was if I fit the model I just described, and I look at the capability parameter, how well does it predict the rankings? So mostly here, the claim I want to make is that this matches existing classic approaches for evaluating model capability. And I'm showing here that we have very high correlations, effectively correlation of 1, between the model fit approach for estimating capability and the basic direct averaging. So this is mostly a sanity check saying things work well. The other thing we do is we check how well this capability measure works when the data sets are non-overlapping. So we intentionally look at 10 random models, and we separate out data sets that don't overlap between the 10 models. So again, this would be equivalent to asking, in this room, you questions, and asking different questions to different people, and trying to rank how well you might do on this exam based on different questions that you might answer. And the observation here, and we show in the paper in the experiments, is that even with random sampling, the performance we get from basically averaging the results is close to chance. So we get a sort of roughly 0.5 AUC. Whereas using the IRT approach, so using the capability and difficulty disambiguation approach, we're able to get 0.78 AUC from this evaluation. The next thing we look at is this active learning idea. So here, we have a procedure using estimates of the model ability to try to ask whether we can use many, many fewer examples than the full data set to get an estimate of how good the model is. And so I'll leave the details to the paper, but what I want to show here, maybe highlights, so the darker lines are the sort of classic baseline approach, or random approach. The darker lines are the active learning approach. The blue lines are the full data set size. And mostly what I'm trying to show here is the gap between the two. So in some of the benchmarks, we're able to show that I can significantly reduce the number of questions I need to ask. We show that in some cases up to 80% fewer questions while still getting an accurate estimate of model capability. A third thing is looking at question difficulty. So we build a model that takes a question in the benchmark and tries to predict how difficult the question will be. Under the hood, again, this is using a similar kind of estimation approach. And the reason this is interesting and useful is that in order to update your IRT model with new questions, you have to refit the IRT model. And this refitting the IRT model can be expensive once either the benchmark questions, you have a large number of benchmark questions, or you have many test takers. And what we show here is that by predicting difficulty, we can amortize the costs and end up having much fewer overhead, much less overhead for trying to update the model with, update the setup with new questions. One other thing to mention here very briefly is that we also look at using the content of the question for predicting difficulty. This is interesting because a lot of the classic psychometric approaches to this question only use the fraction of correct responses. So roughly, a question is difficult as many people fail the question. The question is easy if many people pass the question. That's most of what the sort of existing frameworks do. And what's interesting about our approach is that we, and there's some other work that does this as well, but we use the content in addition to overall performance as a proxy for understanding difficulty of various questions. And we find that this helps much better performance. And so we do this, again, on the same data set on Helm, and we show high correlation between predicted difficulty and the true difficulty of the question as measured by sort of fraction of correct responses. Finally, I want to mention some work we did trying to generate new questions. So the idea here is that you give me the difficulty targets. Here's how difficult a question I want to construct. And I synthesize a new question that matches that difficulty. So again, this is done typically by humans with very careful question construction. What we try to do here is ask, can we use a model to synthesize new questions matching a certain difficulty? And we showed that this can work quite well. So under the hood, we do a combination of supervised fine-tuning and PPO, if you're familiar with this from reinforcement learning, and show that this ends up being an effective approach to synthesize new questions, matching a target difficulty. So here I'm showing some example questions synthesized by the model. So new questions tied to some difficulty targets for both the MMLU benchmark and a benchmark called AirBench, which is tied to safety. And so what we show is using this approach, we can get pretty high performance of both synthesized questions as measured by the quality of the questions using, again, some measure of difficulty and how well we're fitting the target metric. So what I find interesting from this is, again, using some existing tools like item response theory tools can significantly improve reliability of our evaluation processes. I think interesting for us are being able to disentangle various factors that go into model performance. Here I focus on the simplest case, disentangling capability from difficulty. This can go much deeper, a bunch of different constructs that we can try to disambiguate, again, tied to trying to understand what leads to models being better or worse in various kinds of observations. We also use some active learning, so we can show that we can reduce the number of questions you might need to ask to get at a good measure of performance for different kinds of models. Okay, finally, I'll talk a little bit about proposal number 3, which is to learn to predict the effect of model interventions. This shows up broadly around science. I think there's an interesting version of it that's sort of very specific to the AI world, where we want to understand the effect of various kinds of scaling. So things like scaling data, scaling computing, scaling things like model iterations. I find that often a productive way to engage in this looks like post-analysis of data artifacts. To me, I find this is interesting because it actually is a meaningful norm change within the AI ecosystem. So I say, as an example, this looks a bit like, say, data science and the physical sciences. And the reason it looks like this sometimes is that the experiments themselves are so expensive that we can't run them a bunch of different times the way we would normally do. So experiments are run once, maybe, by some large, well-funded institution. There's some artifact that's sent out, and we have to do post-data analysis to understand what we're getting from those experiments. And so this kind of motion, I think, is new in the AI world. I think we're much more used to a different way of data analysis. But often this is the way that we have to do things like scaling analysis. So if we're trying to ask, how will models do when we really, really scale up compute and data and these kinds of questions? Now, we're definitely at the point where academics can't run many of these experiments easily. So we're dependent on sort of data access from some open models of large institutions. Nevertheless, I think there's some interesting questions down this line. So questions around things like scaling laws. There's a bunch of work we've done and others have done on data and compute scaling laws. I'll talk a little bit about some of our work on something called model collapse. Let's see if some interesting sort of connection there. So model collapse is this phenomenon that has been argued to occur that says, when I train my model over generations, eventually the models start to break down. So the idea is I take my data sets, I train model on it, I synthesize data from my model, and I train the next generation of the model based on just the synthesized data. And so there's a bunch of news stories, you've seen many of these, that have argued that this is sort of the thing that will break the entire enterprise. That AI models are going to stop working because, again, they're going to be trained on this kind of synthesized data. And so we looked at this question recently. One more QR code that I think trying to ask questions, to what extent should we believe these claims of model collapse via iterations? And to be clear, this has been done both by researchers and sort of broader industry and news. So I mostly showed news stories, but there's a bunch of academic work that has also tried to ask questions about model collapse. And so on the alarm side, again, this idea is if I iterate on training with synthetic data, I expect the model to degenerate. What we found is that there's actually there are quite a few different definitions of what it might mean for models to collapse. And this lack of specificity actually makes it quite hard to engage with the question. And in fact, the same paper will have 2 or 3 different definitions of what they mean by model collapse, which actually makes it quite hard to sort of narrow down on what's going on in the models. In my view, I think this is an example of certain kinds of validity failures, and has led to consequential validity in terms of downstream worries about some of the aspects of iterative training on models. I do think there are issues in training on synthetic data, but I don't think it's the ones that have been highlighted in the media. And so in the paper, we do a deep dive and look through a bunch of different definitions, and again, show the variety of different definitions and the ways that they often conflict within and across papers. And to my mind, tying back to the beginning of the conversation, so to my mind, there's a bunch of different gaps. There are content validity gaps in the ways that the studies have looked at what it means to simulate the process of synthesizing and training on data. It looks very different than the current practice. In particular, a lot of studies assume that you're going to train only on synthetic data. But in practice, you train on a combination of synthetic and real data. And we show, actually, that this changes the dynamics quite a bit, and so leads to very different conclusions. We think there are some constructability failures here. Part of this is just the lack of agreement. So we use the same word. We all call it model collapse, but we actually mean 8 or 9 different things. And maybe I'll just stop on the consequential validity. And to me, I think this is maybe the most pressing. I don't think the average error of models over generations is actually the key issue. We know that models are good at capturing population behavior, bad at capturing tails. Tails here would mean underrepresented groups of various kinds. And in fact, I think the much more worrying concern from training on synthetic data is that models will just tend to ignore more and more underrepresented groups in our data set. And so we do a bit of work on this. There's other work that we cite in the paper looking at other folks that have studied this kind of question. We think this is actually the meaningful question on training on synthetic data over iterations, much more so than the model collapse story as shown in the media. Okay, so to summarize this, again, we looked at this idea of model collapse. I think this idea of interventional prediction is an interesting one for AI in particular. I think validity plays a key role here, can help us understand and better contextualize the claims. And I think among all the different questions, scaling laws often end up being one of the very interesting ones. As mentioned, often tied to resource allocation, governance, and various kinds of decision making. So I'll move on from the key ideas to maybe some open questions. So if you're looking for interesting open questions to engage in, here's some other ones that I think are very interesting. We're doing a little bit of work on, but I think the field, there's enough gap here that I think there's a lot of work that the field should be engaging in. So one is understanding links between capabilities and upstream behavior and downstream real-world impacts. So right now, most of the benchmarks are built to try to capture something about upstream capabilities. Again, questions about intelligence and reasoning. There's very little work that anchors strongly on what it means when deployed in the real world. And even less so work that tries to capture what the connections are between how good a model is in the upstream sense and how good it is in downstream. And so I think some of the open questions here include much more work on downstream evals, and also this, I think, scientific work that tries to link the upstream and downstream to each other so we understand how things are connected. In particular, I think this is interesting for trying to do some predictability. So the better we can understand the links, the better we can predict ahead of time potential downstream consequences as we have upstream model improvements or failures, and the other way around as well. Have downstream performance help inform what we should be measuring upstream, so we can understand new ways of understanding model capability and potential risks. Another open question is our dependence on multiple choice question answering. 90-something% of the benchmarks that we use in the field are all, I'm going to ask a question, I'll give you 5 options, pick the best one. This makes sense for models because it's scalable. because you can just run this as many questions as you like. We think this has quite weak constructability and ends up with a lot of the issues that are brought up are actually directly tied to the fact that we rely so much on multiple choice question answering as the way that we evaluate AI models. There's some work that tries to engage with this. There's some, for instance, work on AI as a judge, LM as a judge, things like that. I think they're interesting. Early signals suggest they're not enough. There are a bunch of gaps. I'll cite this Dorna paper that engages with some of the limits and the AI as a judge infrastructure. We're doing a little bit of work trying to use information theoretic ideas to see if we can improve upon AI as a judge as a way to get sort of scalable evaluation of model capabilities. So I'll mention some work, but I'd say very early, and I think a meaningful open problem for folks in the field to maybe think about. A lot of the work in psychometrics was really built to measure human behavior. And so one worry that I have, and I'll just say it explicitly, is that some of the priors in how we build psychometrics models may actually sort of implicitly be based on what humans do and may or may not capture what AI models do. So some of what we know and some of what causes concern are things like, we know that the adversarial sensitivity of humans are very different from the adversarial sensitivity of models. For example, if I give you a question, I ask you a question, and I randomly capitalize every other word, you're unlikely to give me a different answer. Many AI models will give, if probed appropriately, would give different answers if I capitalize randomly or add random exclamation points to the end of a question. There's something that humans are not vulnerable to in the exact same way. There's some concern about the extent to which some of the assumptions that are built in, so some of the smoothness assumptions in particular, that are built into psychometrics models, might be implicitly anchoring on human priors and may or may not transfer to AI models. And so there's some work to be done in trying to better disambiguate in those directions. Finally, I think we need a lot of institution building. So what does it mean for more civil society engagement in AI evaluations, both in terms of setting our targets and in critiquing the outcomes of our evaluation processes? So the questions that go all the way from value judgments, what kind of capabilities do we actually care about? What kinds of risks deserve more work on measurement? More contextualization, which perspective should inform the design of evaluation processes? How does measurement shape the different balances and shape power dynamics? More work on institutional structures. How do we think about funding evaluation research? Who has access to evaluation infrastructure? What do these things look like upstream, downstream? If you want to learn a bit more about this, I wrote a paper with some colleagues. Again, another one that's sort of up recently called Towards Evaluation Science for Generative AI Systems that engage in some of these questions. So I think there's a path forward, and I'll say some of what I hope many of us can take from here to move forward. So for researchers, I think we need to be much more careful when we make claims about evaluation processes and benchmarks, to state what they measure and don't measure, and make precise arguments for why those things might or might not be true. We need to think through validity more carefully, not just thinking about scoring, and think about theoretical process for connecting measurement to capabilities. For industry, I think there's a lot of scope to invest in evaluation infrastructure beyond leaderboards and try to ground capability claims with appropriate evidence. And further, recognize limitations of benchmarks as a main driver of performance. For policymakers, I think a lot can be done by policymakers demanding that when we make claims, those claims are actually valid claims. And so demanding more evidence for claims about capability of models, I think could meaningfully move the needle. There should be more diversity in the way we think about evaluation approaches to better cover the landscape of ways that we can measure models. And thinking about ways that we can, again, fund potential independent evaluation research, that we have better coverage. And then for civil society, I think there's a lot of scope to engage in defining what it is we want to be measuring, particularly downstream. And a lot more scope to be critiquing unsupported claims of capability or safety from existing AI models. So I'll summarize here. I went through 3 main ideas and some open questions. So ideas on thinking about measurements and tying it to specific claims. Ideas on existing tooling from various fields, in particular psychometrics, that I think could help improve AI measurement. And some ideas on predictability of the effect of model interventions and AI infrastructure. Okay, I'll acknowledge, and here's a link to the slides if you're interested. So the first is my group and some of our friends and collaborators, and a bunch of funding, including from HAI, MacArthur Foundation, and a variety of other organizations. Okay, thank you.
Yeah, thank you for this great presentation. I have 2 questions, actually. First question, if you will apply, everybody claims there's AGI coming, right? Artificial General Intelligence. If you apply this approach that you just presented, how will you go about measuring that, if that will be something you would do? And then secondly, if you will operationalize this approach in terms of validity evidence, how would that run, if you apply that into, let's say, ChatGPT before you even answer the question? How will you operationalize that, before you ask the question to ChatGPT and before ChatGPT answer and pose that question to you? How will you operationalize that so it happens in real time?
Okay, I think I'm missing the second question. I understand the first one. Could you expand a bit on what you mean by answering before it answers?
Right, so if you would then apply this approach, that every answer that ChatGPT will provide you will actually run through this vetting system.
Mm-hmm.
And in that way, then whatever it says is actually backed with a claim. So
okay. So the claims are not. I'll do the second first. So the claims are not a level of responses; they're the level of evaluations, right? So the claims are claims we want to make as either broadly stakeholders or people who are engaging in trying to understand or deploy systems. So I want to make a claim: this model is good at, I don't know, answering patient questions in a healthcare setting, or broadly, this model is good at medical knowledge, which is a much richer, broader claim. At that level of abstraction of claims, the task is to find evidence through evaluations of various kinds, support the claim that you're trying to make. So it's not at least the way I understand your question, not the level of single responses, that level of sort of generally claims of capability and safety for AI models. For the first question, what does this mean for the AGI question? I think there's not good scientific support for trying to say this. But I think that there's a path towards doing this. So you asked me, what would I do? I think the work to do here is a combination of making the construct concrete. I think often some of these questions are stated without preciseness or detail on what we actually mean. So what do you mean by AGI? And then once you say that, what are the things you need to measure around it to be able to make that a concrete statement? So that would be the nomological network to build around this. Then you have to ask questions about what evidence do I need to see, and how do I argue that this evidence actually supports my claims about AGI. So in the paper, we have some references to work that's been done. I don't think this work has been done in our field in AI yet. There is work in human intelligence that asks these questions. I think one, depending on where you sit, either amazing or terrible thing about this process is that this is really a scientific process, and what this means is that it will iterate. We'll learn more things, we'll change our assumptions, we'll break some old assumptions, we'll create some new ones, and this iteration I think is healthy. So if you like the scientific process, this is awesome. If you want certainty and a direct answer, this is annoying. But I think this is what the world is. And again, this iteration of scientific process, getting new evidence, trying to make those claims concrete. In the paper, we have some discussion of some examples from other places that can maybe help shape this discussion. Good question. Thank you.
Great. We'll go to a question now from the online audience. Most benchmarks focus only on accuracy. What work is being done on efficiency benchmarks like power and time needed for inference, or data and training time required for accuracy?
Yeah, so there's a super interesting question. There's a little bit of work on trying to move beyond pure capability. So think about resources broadly and what resources, so understanding models. I think this is important for downstream use cases, understanding resource trade-offs for different kinds of models. So as many of you might know, models can be expensive in terms of the backend compute that we need to put in, the size of the models, so this size, often I guess tied to compute, the data resources that we need to put in them. There's a bit of early work trying to ask these questions. There's some work out of ML Commons that thinks about benchmarking to capture trade-offs beyond pure performance, but also asking, say, resource inputs, so computing power, things like that. I would say it's very early, but I think the more we're looking at downstream applications, and in particular applications where compute may be limited, or we're worried about impacts on resource inputs, so climate and things like that, then I think these are extremely important questions to ask. I think we're very early in trying to ask these questions in the field.
All right, let's do another audience question. It looks like there's one up front over here, and the mic is going to come in a second.
Thank you for the presentation. One question I had is, a lot of these models are eventually going to be used in the context of a particular application with application-specific goals. And maybe there's a application-specific claim, and then you want to go and figure out which model or combination of models would be best suited for this particular context. In that environment, like each claim is going to be pretty unique. And so how would you go about looking at evaluations which were designed to measure things that are very likely not going to be a one-to-one match with what you're doing? How would you leverage these evaluations to make a business decision?
Yeah, so I think one of the open questions, and actually it's what this question tries to anchor on, is this gap between the upstream and downstream. So again, if you're going to focus on high-level capabilities, what does it look like in a particular context for a really impactful setting? Again, I don't think we know how to do this well yet. Right now, the answer is you build an evaluation process in the context that you want to apply it. And so this scales with number of contexts you want to apply things in. So this is fine, but also expensive, and unlikely that we can do this for all the contexts that we care about. And so some of the work that we're starting and we're hoping to do more of is being able to make these predictions much more accurately. So being able to link upstream and downstream without having to as directly evaluate on the specific downstream. But yes, very important question. Right now, we don't know how to do it as a field.
Another question from the online audience. Thank you so much for an insightful talk. Could you elaborate a bit more about correctness in relation to benchmarking? More specifically, in the philosophy of computing field, there seems to be a worry that it is much harder to claim that an ML model can be said to be correct.
That's a fascinating question. I wish I could get more context, but I'll speculate based on what they actually said. So I guess there's a narrow version of correctness, which is just answering a question. I think, questions can be right or wrong for some questions. I think not every question, of course, has a right or wrong answer. So there, I think things are fine. I think there are more complicated cases where one is trying to use AI models for things that we typically use sort of explicit, so I'm thinking of reasoning applications and things like that, where we have ways of checking correctness and verifying correctness. It's tricky and fun, but various kinds of reasoning tasks where there's a well-defined notion of what it means to reason. We have very defined notions of the correctness and sort of some kind of complex reasoning settings. I'm thinking of applications to, there's some versions of game playing, there's some versions of things like SAT solvers, so computational solvers of various kinds, arithmetic sometimes, where there's a gap between people using it sometimes for these kinds of tasks and sort of how likely we think that these models are to be able to solve these kinds of tasks out of the box. I think some of the argument that comes from that literature suggests there are very fundamental computational reasons why we should expect there will always be some gap. What I mean, this is to philosophize, because the question was partially philosophical. It's connecting to things like P versus NP. So, like, can I answer NP kinds of questions using non-polynomial types of questions using polynomial time. And in particular, AI models, they use finite computing and they answer questions that we know cannot be solved without sort of more sophisticated or harder compute investment. I think the rough answer is, for those kinds of questions, we think, observable performance suggests we can approximate things pretty well. So if I restrict myself to like specific applications, I think the arithmetic one is actually a fascinating example of this, where models do a reasonable job in very basic arithmetic, so adding numbers, multiplying numbers, things like that, close to where they're trained, and then start doing really badly once I ask a question, like ask to add or multiply a number that's sort of much, much bigger, much, much smaller, so out of the range of data that the model has seen. And I think this is actually a version of this question. I think in distribution, so close to the training domain, models can be good at this. Out of it, I think all bets are off in general. It's probably a bad idea to like do an unverified deployment of an AI model on a problem that we know should be hard, where context will matter a lot. If you have verification, I think there's some productive ways to go forward, like verification in the loop with the deployment process. Without verification, I think there's a higher risk of failure. So that's current opinion, I guess, in this direction.
Great. I think we have time for one more question, and it looks like there's one right in the back.
I wanted to understand your definition of what is a difficult question. Is it more on the lines that, is it touching all the different data sets that are available? Is it sort of doing any answering based on emergent behavior? Is it doing reasoning to answer the question? Can you give some insights into what would be considered a difficult question?
Yeah, so to first approximation, a question is difficult in a population. Actually, you can anchor this to say for student learning. One way to think or to check how difficult a question is to ask how many people correctly answer that question. So if you have some population of whoever you consider a reasonable distribution of students in terms of capabilities, then if the question is answered correctly by most of the students, then it's likely easy. If a question is missed by a large fraction of students, then it's likely harder. And so to first approximation, difficulty measures, the actual thing that's being done is a late-driven model, but the first approximation is capturing roughly the fraction of models that get the answer correct. I think at a high level, this is a good sort of working intuition, is that the big signal that ends up defining difficulty to a large extent is sort of fraction of correctness. Again, I think one nice thing about this is you can also do this separately from the modeling. So we've done some other work where we've looked at in this case, we're trying to do scaling laws for test time computing, and we separately looked at difficulty based on fraction of correctness and show some interesting relationships. I'm happy to share a paper offline. I think in a population setting, you can get at a bit more signal than that by using both the content and the fraction of correctness, so what the actual text of the question says. But the first approximation, at least for building a mental model, you can think about this broadly as question is difficult if most test takers get it incorrect.
All right. Well, thank you very much for a great presentation, and have a good day, everybody.
Thank you.